that's not what he's going to be talking to us about. He's actually going to be talking to us about pipe and filter style and how that can be refined so that we can, in fact, understand and use better various incarnations of the pipe and filter style. So he's also a very short guy, as you can see.
All right. So just so you guys know, there is a handout here. If you don't have it, this is basically all you need to know. So feel free to leave right now. Just grab your handout on the way out. Yeah. So does everybody know about the Academy Awards, the Oscars? Show of hands. Who's heard of the Oscars? Right. And so who here has also won an Oscar? So I get this email all the time. The subject is Oscar with a question mark, and it's from some recruiter, and they want me to, join some whiz-bang startup. So my background, I'm not even a computer scientist, truth be told. I studied brain and cognitive science at MIT. And this actually applies here because one of the things I think is really useful for the software architecture community is adding the value of language, terms, really making things accessible. Because once you can sort of distill things down into that, then people can use it, right? That's what design patterns did. And so I think I here have some terminology and some shapes, right? And the whole idea here is the two-word summary is prefer push to pull, okay? And I'll show you a way to draw this on the whiteboard that makes it really useful when you're talking about systems. We were talking, the last lecturer was talking about these systems, and he was talking about multicast and then things that would go and sort of pull things out and move them around and so on and so forth. And in my head, I'm drawing these pictures on the whiteboard as he's talking. So the email says, hey, I'd really like you to join my startup. And by the way, did you really win an Oscar? As if that's important, right? I mean, SinkorSwim, this is fun. This is good stuff. This is really, I think, something useful. But the Oscar, it is pretty unique, though. So yes, it's true. That was me back in the day. We did have a bit of an award ceremony. It was a little bit like Star Wars, though. It was in a galaxy far, far away from any actual movie stars, but we had champagne in the corporate cafeteria, so that was kind of neat. So since Avid, and Avid's really where I started to think about data streams and movement through systems. We're really obsessed with getting 2 streams of uncompressed video and 8 streams of uncompressed audio ripped off of a hard drive and out to the screen, which back then was really, really hard. And this is some of the places I've been along the way. At Amazon, I learned about PubSub and interesting stuff there, then left there and did some other startups and stuff. This is talk. It's called SinkorSwim. And so I'm going to give you a hint on these diagrams. You'll see these are actually the diagrams. It was published in 2006 on my blog, ivanism.com. So you guys are probably familiar with the pipe and filter. You draw a box, you draw lines between them, the lines connect the boxes, and really the magic happens in these filters, right? SinkorSwim actually flips that model and says it's pretty useful if you actually pay attention to the way these 2 boxes are connected together. So this is an example of SinkorSwim puzzle pieces for parts of my career. It's neither complete nor necessarily to scale, although the connections between some of the various companies are true. Once you decipher what the puzzle pieces mean, that may help you out. So at Coco Communications, actually, we did some work. It was an ad hoc mesh networking protocol, and we built streaming video and voice systems, some of which for the Navy and Coast Guard as well, so that was pretty neat. And used UDP and all that good stuff. And this was great because this, I sort of started this company with some folks, and we built this thing called the asynchronous processing engine, where we actually built the SinkorSwim puzzle pieces into the software, and people could instantiate various different types of puzzle pieces and automatically combine them together based on the rules that you'll see. Yeah, that was called the asynchronous processing engine, or APE. But it was cool, but not very typical. I mean, how many people get to just start a company and build some cool shit and fly it out? At Click, I actually went, and they had a totally different problem. Here was an existing company. So at Coco, these systems were running on handheld, it was called the iPacs at the time. It was like a tiny little ARM processor. We're running an embedded version of Linux, but we were able to do video and voice on these tiny little things. Click had a desktop Windows application trying to do peer-to-peer video chat, and their CPUs were just hogging up the whole machine. They're running out of memory. They're like, what is going on? I taught them the SinkorSwim architectural style, and they were quickly able to realize that they were using these anti-patterns that I will show to you, and making just structural changes to the way they were doing things, simplified their system orders of magnitude. I think it was like 70x on memory and like 30x on CPU. It was like massive, okay? That's 30x, not 30%. So, now I'm at Google. There I did the product that just got released as Google's Cloud Pub Sub. And so, publish, subscribe very much fits into this model. So we're going from pipe and filter to these SinkorSwim puzzle pieces. And again, it's a way to draw the pieces on a whiteboard, and also each piece has a name. Okay, so here's how this talk works. I'm hoping, that's the whole thing on your sheet. So I'm going to try to be entertaining, not waste your time. The important points will be accompanied by pictures of sinks. So when you see a sink on the screen, pay attention. All right, then we'll take a quick break. You'll see a beautiful pool, and then we'll come back to the content, all right? There's a pool on this. All right, so streaming media example. So, you can imagine somebody broadcasting a podcast and somebody on the other end listening to internet radio or something like that. And you can use these pieces to decompose them. You can actually go to the whiteboard. Unfortunately, I don't know if I'm allowed to do this, but you can actually draw the pieces here. So on the top, we've got a podcaster where we've got a sound card. And the interesting thing, so I tend to draw the pieces like that. The interesting thing is you don't necessarily get to choose the shape of your endpoint, right? The endpoint might be push, might be pull. But you don't necessarily get to choose that, right? The question is, what do you do from there? So you take what you're given, and then you try to be efficient. Now, the other thing, too, is there are times when you may want to use these resources for something. There may be a reason why you've chosen to add a buffer or add a timing loop, because these are the two resources that come into play here, memory and CPU. So we have a sound card, which actually works as push, and so then I run it into a codec, and so on and so forth. So I can draw these puzzle pieces with little arrows pointing out or arrows going in, and I have to match up the arrows on the whiteboard, okay? So podcast listener, here you see it's much more complicated shape where I have some shapes that have things like buffers and timing loops, and that's just a function of the way these systems are coupled together. So this is an indoor pool. Okay, so here are the four terminal pieces, right? You either have a source or a sink side. Now, we'll pay attention. We couple an output side of one piece to an input side of the other. And you just want the arrows to line up, right? So here I do it in ASCII art, but you can draw it on the whiteboard. Greater than lines up with greater than, less than lines up with less than in the ASCII art, right? So this is the output side. This is the input side. Things on these diagrams flow in this direction. Now, if it points into the box, that's asynchronous. That's the passive side of the world. So the asynchronous side is passive, and it's just kind of waiting there for something to happen. The synchronous side is what controls the interaction, and that's the side that's pointing out of the box. This is an artsy pool. All right, so here we have these are the smells, right? So in this architectural style, we've got certain smells. These are what you want to look out for. If you have a synchronous input, which means you've got a pull. This is requiring a timing loop. So just the fact that I've got the pull interaction right there requires a timing loop. So this is a potentially bad smell, and this is the problem with the microphone. So the way the synchronous input works is it's kind of standing there, and it's controlling the interaction. So it's saying, do you have something for me? Do you have something for me? Do you have something for me? Takes a lot of energy. We have an asynchronous output. Asynchronous output also, again, this is a smell. It needs a buffer, right? So some stuff comes in one way or another, and it just has to hold on to it. Has to hold on to it until a synchronous pulls it out, right? There we go. So these are the code smells, and I'm not sure why that sign is up there, but you want to avoid those shapes if possible. There we go. And this is a violin-shaped pool. All right, so here we go. This is a very pessimistic diagram right here, right? So we see we've got buffers and timing loops and so on and so forth. But the piece highlighted is an adapter. So again, you don't necessarily get to control the endpoints. It might be that you have a sound card that is just going to pull data from you as soon as it wants it, or that you can just add stuff to it. You might find that you've got a web service that works, by AJAX, and so you just have to throw something at it, and it's got to accept it as soon as you send it, right? So you don't necessarily get to control the shape of the endpoint. So you may find in this example where I've got a synchronous output and a synchronous input. So I need an adapter, right? And this adapter requires a buffer. The other adapter is where I connect two asynchronous sides, and this one has two synchronous sides to connect them together, right? So these are your adapters. And with that ape at Coco, we were able to automatically build these. So there you go. Those are the two flows I just showed you. This is a nighttime pool. All right, so each of these pieces we could name. Now the names, all right, so I don't know if you guys are aware, but there's actually a SinkorSwim, the latest craze, right? The latest dance craze in all the clubs these days. My teenage kids love this. It's the SinkorSwim dance, okay? So here we have a well, and the whole idea between a well is you have to dip your cup in and pull something out, right? So it has to store, right? Your well is a storage. You dip your cup in and pull something out of the well. Then you've got the driver. The driver has this timing loop, and it says, do you have something for me? Here, take this. Give me something. Here, take this. Give me something. Here, take this. The pool is passive, right? It's just this big, giant thing where you can dump cups in or pull cups out. And on the end, you have your drain. Your drain is this active. It's like a vacuum. It's like sucking stuff away. Give it to me, okay? Now, rewrite rules. This is pretty cool. There's sort of a fractal nature to the SinkorSwim, where depending on what level of abstraction, you can look at things either in aggregate or decompose them, right? So this is kind of useful because we can actually take something that's the wrong shape and change the shape, and you'll see something very cool about that in just a minute. But you can also look at things at different levels of abstraction. Now, we're software architects, so we like thinking about things, right? So at the high level, you might have your web service over here, your browser client over here, your database over here, and you can actually draw the puzzle pieces for how those interactions happen, right? Who's controlling the interaction? Which side? Is it push or pull? Right? But then we can go down and we can look into that. Okay, here's my web service. So a request comes in. I don't get to choose the shape of that endpoint. But then how do I process it? What do I do? What are the different services that I call? And then for each of those services, how do I decompose those into libraries? Are those libraries coupled with callbacks? Or are they functions that I'm calling? Is there sort of timers that go off? So you can look at this as sort of a fractal level. You can see the different layers. So this rewrite rule, we combine a driver connected to a pool in that order, and we get a puller. Now this is the worst of all worlds, right? So the puller needs the timing loop and the buffer. It's like, here, give me something, and I'm going to hold on to it. Here, give me something, and I'm going to hold on to it, and it just sort of slowly weighs down. Okay, so this is a synchronized pool. Right. So these are the pieces on your handout, right? These are the ones we've covered so far. Okay, so there's the stream. Now the stream is just flowing, right? The stream is just saying, okay, here, have some. And it's just flowing along its merry way. We've got the pool and the driver. Again, we talked about these pieces, but here it's in the opposite order. And this is exciting. I'll show you why in just a moment. And then we have the sink, right? Remember, the drain is pulling. The sink is just passive. Just takes stuff in and makes it go away, okay? Now, when you have the pool and the driver in this order, magic happens. This is the money. This is the rewrite rule that at click made orders of magnitude improvement. Boom. Well, there you go. So we got rid of the buffer and the timing loop just by combining them. Just by combining these two pieces, we got rid of both memory and CPU resources. Didn't change the functionality at all. Not at all. Changed the structure, got rid of the resources, right? Orders of magnitude improvement at click. Right? This is the difference. This is why Cocoa we could run in a handheld device without a problem, why click was grinding to a halt, right? Cocoa and click. All right? This is a diving pool. So those are the pieces we just saw, right? And now we're swimming. Okay, so this has actually been formalized by Bradley Schmerl at Carnegie Mellon, who I actually have not even met, but thank you, Bradley. He put this into a program called Acme Studio in cahoots with my friend George over there. And they actually built this out. And what's cool, this is the sound card, the internet radio example on the top here. So we've got the network interface card, the packet handler, the jitter buffer, the codec, and the sound card. So we're playing internet radio. And on the bottom, he shows that if you try to connect a pusher with a drain, it doesn't fit. The puzzle pieces don't fit together, right? And so we know we need to put one of those adapters in there, and this highlights it. So this is amenable to static analysis. Pretty cool stuff. So there we go. We've gone from pipe and filter, where we focus on the filters, to the SinkorSwim style, where we look at the connections, and based on the connections, we can understand resource requirements. We can use that simple rewrite rule to get rid of both the buffer and the timing loop if we do things right. And that's your handout. So where do we go from here? SinkorSwim is the very simple pattern, very simple architectural style. But you can do more things. So the thing that I didn't mention about the ape before was anytime there's a timing loop, the asynchronous processing engine actually had a controller. And the controller sort of sat on top of these puzzle pieces. And anytime there was a timing loop, it actually waited for the controller to go and poke it, right? So we can control the flow and the timing through the system if we wanted to. And it worked like a scheduler. You can actually go one-to-many. Maybe this is called diffusers or something, right? So this is, for example, in Google Cloud PubSub, where I publish a message on the bus, and I've got many subscribers, right? I've got a lot of people who are interested in a particular business event, and so they're all going to do their thing, right? Somebody bought a book, and now all of a sudden, everybody's got to update their stuff. You can think of many to one as combiners, right? And this could be the logs example that Patrick talked about yesterday, where I have a whole bunch of people publishing logs, right? And then I've got one place that they all ultimately have to wind up where I'm going to aggregate them and do stuff. You can think about many to many or things like that. Input to output ratios, you can think of like a gearbox. Maybe I need three sets of input from a sound card to plug it into the codec or something like that. The other interesting thing, and this is going to bring us all the way back to that Oscar, is if you think about the blocking behavior and the timing behavior of these puzzle pieces, right? So you can use that as a control point like we did with the ape, or you can say, hey, this is really important. Whereas in Avid, we were just obsessed about getting things moving through the system as fast as we could. We were obsessed about trying to avoid media underruns, which meant that the system couldn't keep up, right? And when that happens, your buffer is going to overflow. So this is another interesting aspect that you can look at. And that's all I got. Any questions? This interaction right here is what's causing the requirements. The asynchronous input doesn't have any requirements, and the synchronous output doesn't have any requirements. Remember, in the dance, this is just like, you're just waiting there passively. Oh, here's something. Thanks. Here you go. Thanks. Here you go. Right? So it just flows. I don't have to worry. I'm just sitting here passively until somebody hands me something. Then I hand it off. Right? So the problem was in here, somebody handed me something, and I had to hold on to it and wait for the next guy to come and grab it from me.
So don't you have the potential though to leave the buffer the next input while you're handling it, the other one is not? You know what I'm saying?
So right, I mean the asynchronous input, if every time something comes in I can immediately hand it off, we're good to go, right?
Yes, that assumes that you can hand it off before the next.
Correct, right? So you need to make sure that you have the throughput that you
Right.
need. But if you can do that, then you don't need to buffer, right? And this is the interesting thing. You don't always get to choose that. Sometimes you may need the pool because you're changing the timing on one side or the other, or you can't couple
That's
them.
what I was thinking of.
So there are times when that's necessary, but not always, right? A lot of times it's just not. You can just hand off the next time. You do a quick process and you hand it off. And if you can do that quick process in the time frame required, you're good to go. It's also interesting because sometimes these pushers have a small, fixed size internal buffer, right? So that doesn't matter. That actually doesn't matter, right? Like, you probably know that your sound cards and your network interfaces and all these things, you know, your CPUs have registers, right? As long as it's fixed size, it actually doesn't matter. What matters is if there's an opportunity for it to grow, right? Because that's where you get resources that start to degrade. So maybe I have a thing here where I've got a piece that takes, like I said, a certain amount of input and then, you know, spits out a smaller amount of input. For example, a codec where I'm encoding, or a codec where I'm decoding, where I get a lot of, where I get a small input and I produce a larger output. That's fine, right? And I may need some internal space to do this. I may need some internal CPU to do the processing. But I'm not having space or CPU just on the basis of the way these things are connected. Right? And that's what we're talking about here. These resources, this is just based on the way they're connected, not based on what's actually happening inside the filter. Right? Your filters still do all the things that they did before.
Yes. So this gives us a much richer dramatization, even a lexicon of what goes on in pipe filter. Could you actually codify this in some way so that I understand what the assumptions are? Because we just talked about several conditions, when I use it, when I not use it. Is that somehow written up, or in the Acme formal specification, is that all somehow codified so that I could understand? design patterns book.
Right.
Okay, now we had all the names and people had intuitions, but underneath those names, there was a template. And the template described what's the problem, what's the solution, under what assumptions would this be useful, what are the consequences of using that.
Right.
And it strikes me that you've taken pipe and filter and done a refinement that's very useful with a clever lexicon and even some dramatization. But if I don't remember all of your dramatization, and I'd like to think, where could I go and find out? Where could I go and find out exactly what were the assumptions again? He said, when was it that I wouldn't have used this and I'd still want to use the old thing?
Yeah, I mean, I think the best thing I got for you at the moment is this handout, right? Which shows you, based on the shape, right? This is just based on the way things are connected, what resources the shape requires.
Okay, all right.